All right, we're starting a new chapter today, chapter 8, and it's all about triangles, right? Circles. Okay, we'll talk about what a chord is here in a second, but it's all about circles. A whole entire chapter about circles. You probably never thought there was that much information about a circle, but there is. There's a lot of stuff to know about circles. So let's draw a circle here, and we'll just talk about a couple things. We've actually done a lesson in the last chapter on circles, didn't we? What did we learn about circles in the last chapter? Circumference, area, radius. It's not a apophthegm. Yeah. Well, it's from the center, perpendicular to one of the sides. Okay. So we've learned a little bit about a circle. So let's do a little bit more. First of all, see that dot right in the middle? What do we call that thing?
The center.
The center, very good.
Wow.
Okay. So, and we, by the way, let's do this. If we wanted to name the circle, we didn't talk about that in the last chapter, but we will right now. Let's see. In my notes, I didn't put any letters. Let's just call it A. Is that all right? So if I say that point in the center of the circle, this is called the center. Okay, it's not the middle. All right, it's the center of the circle. This is how we name the circle. You know how we name triangles with 3 points, we name rectangles with 4 points and all that kind of stuff. Okay, we name a circle with just 1 point. And where do you think that 1 point is?
In the center.
Very good. It's in the center. And this is how we name it. We name it circle, and watch. We draw a little circle, and we put a dot in the middle of the circle. Right? That's the, what's the word? That's the symbol. That's what I'm thinking of. That's the symbol for a circle, right there. It's a circle with a dot in the middle of it. Okay, the dot, what do you think the dot represents? The center, right? And then we name it circle A. So this is how you would say this, okay? You would say circle A. Everybody got it? That's how we name a circle. Pretty simple. Everybody's got 100 so far, right? Yeah. All right, so let's talk about a couple things that we've already discussed in the last chapter. So if I draw a line segment from the center to a point on the circle. Now, when I say on the circle, a lot of times you might think of this as a disc, right? And I play disc golf, so I have a lot of discs. I should have brought in a disc. It is fun. It's my favorite sport now to play. So a lot of times we think on the circle would be like on the disc itself. Everybody watching, or a plate or something like that. Okay, you'd think that on the circle would be like right here, right here, right here, but it's not. On the circle is actually on that white curved line that makes up the circle. Okay, that's the actual circle. Everybody got that? So this would be on the circle. This point out here would be outside the circle, or it would be give me a good geometry word that we've discussed before. It starts with an E. Exterior, right. Well, it's not an angle. It's just a point. It's just a point. So this is the exterior of the circle. Where would a point inside of here be? It would be the interior, right. This would be the interior of the circle. This would be the exterior of the circle. This would be what? On the circle. Very good. Okay, this is on the circle. So if you draw a line segment from the center of the circle, okay, you guys are all geared up today. It's Monday morning. You should be half asleep, but everybody seems to be a little crazy today. So let's take a look. Let's listen now. Teaching you brand new things. Let's learn this from the very beginning so you don't get lost. So the center of the circle is right here. If I draw a line segment from the center of the circle to any point on the circle, it doesn't matter where on the circle. I could go anywhere on the circle. Okay, it's got to be on that white curved line right there, which is the circle. You're right. That would be called the radius. All right. So that's the radius of the circle. All right. Let's change colors and draw something else. All we're doing right now is just labeling stuff. We're gonna learn some things about these in a minute, but let's just label it first. So what if I did this? What if I went from 1 point on the circle, I went through the center, and I went all the way to another point on the circle? Is it? Well, technically it is a chord, but we'll talk about that in a second. But more specifically, this pink one right there is the diameter. The circumference is not.
Oh wait, circumference is the thing around the circle. Oh yeah.
The circumference is the distance around the circle. That was one thing you were supposed to know because we did that in the last chapter. All right, but that's okay. So this pink one right here would be called the diameter. You're making it very difficult for me to talk. Yeah. Because you were the one that was talking while I was talking. That's why I said you're making it very difficult for me to talk. And you look confused. Why do you look so confused? Because you were. You were talking right in the middle of me describing this. And you still look confused. I don't understand why. All right, so that's the diameter. Let's do another one. Let's draw. Now, Anthony already said this. But I want to go from... Now, what was specific about this diameter? It went from one point on the circle to another point on the circle, but specifically it went through what? The center. It went through the center. That's the diameter, okay? But if I just connect one point on the circle to any other point on the circle, it doesn't have to go through the center, okay? If I just go from one point on the circle, right here, I'm not going to label these, to another, let's do it. Let's call it X and Y. If I go from one point on the circle to another point on the circle, we have a name for that. Take a wild guess what that's called. A chord. All right. So it's called a chord. All right. So when you go from one, it's a line segment that goes from one point on a circle to another point on the same circle. That would be considered a chord. All right. Notice, is a radius a chord? Why not?
Because it doesn't go all the way to the other side.
It doesn't have 2 points on the actual circle. Is a diameter a chord?
No, because it goes straight. It goes through the center.
But it still has things on each side of the circle.
I did say it right. I did say a diameter was a chord before. But what did I say? What did I say the definition of a chord was? It goes from one point on a circle, where? To another point on a circle. Does a diameter do that? Yeah. A diameter goes from one point on a circle to another point on a circle. So is a diameter a chord?
Yes.
Is every chord a diameter?
No.
Okay, because this blue one right here is a chord, but it's not a diameter. Why not? Because it doesn't do what?
Center.
Doesn't go through the center of the circle. All right, we straight on this? Okay, yeah, all we're doing is just naming these things. Okay, we're going to have to know this for sure, all this stuff, as we go through the rest of the chapter, especially chords. We actually have a symbol for a chord, okay? And so I would use the 2 points that it hits on the circle. But I can't just say that, because if I just said that, what does that represent? It's a Y. It's XY.
Just the points?
No, it's not just the points. What if I put... but it's more specific than just the line.
It's the points.
No, come on. We've talked about this a lot. What is it? It's the distance, okay? Gideon, is that what you said? No? All right. It's the distance. Listen. Shh. Guys are in a crazy mood this morning. It's the distance. When there's no line segment over top of it, it means the length of or the distance of line segment XY. Now, I don't know how long this is, so I can't really say what the distance is, okay? But if I'm talking about the chord itself, the chord looks like that. I'm sorry, I lied. I'm talking about the arc. Sorry. If I said a chord is a line segment, isn't it? So that would just be... If I said, what is this chord right here? You would say line segment XY. And you got to make sure you put the line segment over top of it because I'm not talking about the distance or the length of it. I'm just describing that chord right there. Sorry, I was getting a little ahead of myself with the next thing. And we're not even doing that in this lesson. I don't even know why I did that. But I was getting too excited about all the other stuff we're going to learn about this. All right, so that's pretty much it for definitions and for describing different things here. A radius is also a line segment. A diameter is also a line segment. And a chord is also a line segment. Would you agree?
Yeah.
All right, so let's do another one. Let's just copy and paste this. So, there'll be numbers, don't worry. There's always numbers. Okay, what if I did this? What is that? Is it a chord? Right, it's not a line segment. Yeah, whatever he said. All right, so if I call this A and I call this B, I could say that this is a chord. I could call it chord AB, right? Or line segment AB. Would you agree? But this is a theorem. I'm not going to write the theorem down. It's in the book. If you want to write it, you can, but I'll read it to you. Here's what it says. It says, if a line, do we have a line here? Yeah. Intersects the interior of a circle. Does this line intersect the circle? Yeah, because it goes through the interior. Now, there's a reason why they say the interior, because you could draw a line, right, that intersects the circle, but it intersects right there, just at that one point. That's another lesson. That's actually called a tangent of a circle. Okay, we'll get to that. We'll get to that a little later. But we're not going to talk about that right now. But this specifically says if a line intersects the interior of a circle. Everybody got that? So it doesn't just hit one point on the circle, hits 2 points on the circle. Okay, then what must it contain then? What's inside that circle then? A chord, that's right. And so that's what it's actually, I'm sorry, it's not even a theorem, it's a postulate. It's just something that they tell you that's true. You can't prove it. It's just basically something in geometry that must happen. All right, so if a line goes through a circle, goes through it, doesn't just hit at the edge, but if it goes through it, it must make a what? A chord. And what is that chord? It's chord, or it's line segment what? AB, all right? So the line itself is not the chord, but the line segment from one point on the circle to another point on the circle, that would be considered a chord. So that was pretty easy. Let's do another theorem. Now we're really going to get into it. All right, and this is where we have the potential of putting some numbers in here. All right, and we'll definitely have numbers. Don't worry about that. Let me do that. Let me get rid of that little dot right there. Guys, look, I literally took 10 seconds to draw this thing. You guys have already gone off course. Just let me draw it and sit and just watch. It's not a free time when I sit there and I draw something for you just to go off and do your own thing. We've talked about this dozens and dozens of times in here. Please, take it to heart, okay, and actually do what I ask you to do. If I'm drawing a picture up here, just sit and watch me draw it. It's not a free time to have your own conversations. Do you understand?
Sure, yes.
Gavin, do you understand? Because you're the one I'm talking to. Do you understand? Yes or no? Yes or no?
Yes.
Okay. That's all I want to know. I just want to make sure that you're hearing me. All right, here we go. What did I just draw right there? Drew a radius, okay? Now, here's what it says. This one is a theorem, okay? So here's what it says. If a radius, do I have a radius here?
Yes, sir.
Absolutely. If a radius is perpendicular to a chord on the circle. Okay, so what I'm going to have to do, I can't just draw any random chord. I got to draw a chord that's what to this radius? Perpendicular. So let's try to draw it right here. And that looks pretty perpendicular, doesn't it? Okay, so if it's perpendicular, it must be what kind of an angle? A right angle. So this is what the theorem says. Everybody listen. It says if a radius, that one right there, and let's label it. They call that O. A lot of times they call the center of the circle O. You don't have to. You can call it any letter. It doesn't make any difference. But a lot of times in geometry, in high school geometry anyway, they put O as the center. All right, so they do it here. They put this. So the radius is OC. The chord is AB, and it intersects at point D. All right, so we've got everything labeled. Now, here's what it says. That's all the if part. All right, so if we have a radius, and if it's perpendicular to a chord, that's all given, right? It's given that OC is the radius. It's given that it's perpendicular to this chord right there. Then what must be true about the chord? Let's take a look. So what is this chord? It's AB, right?
Yeah.
So what do you think might be true from AD to BD?
Equal.
It bisects it. Very good. Okay, it bisects it, or those two segments are equal to each other. All right. Everybody watch it. Okay, so that must mean if all that stuff's true that I said before, what must be true about that chord? It must be bisected, or these two little segments right here are going to be equal to each other. All right. Now there is a little proof for this. I'm not going to go through it formally. We'll just talk about it a little bit. What if I drew from O to A, and I drew from O to B? Okay, yeah.
Sides made a second.
And what is OA and OB and OC? They're all what?
Radius.
They're all it's not radiuses, it's radii, right? Okay. They're all the radius of the circle, agreed? And they're all the same length. OA, OC, OB would be all the same exact length because I go from the center to any point on the circle, that would be the radius, agreed? So look at this triangle right here. Again, I'm not going to go formally through this, but I want you to see why AD and BD are equal to each other, okay? Because, as students, as geometry students, we shouldn't just always accept things. We should be, if we can prove it, we should be able to try to prove it. We're not going to do that for everything because sometimes it's really hard. This one's kind of easy, so we'll just do it with that. So I've got a triangle here and I got a triangle here. What do you think might be true about these two triangles right here?
They're
Equilateral.
Congruent. They're congruent. Now, why are they congruent? Well, you got one side is equal to one side, right? And you got a what?
second side.
You got another side. See, this side is equal to this, from this triangle is equal to this one. So I've got side, angle, side. Because if this is 90, then this has to be 90 right there. Would you agree? Okay, or, yeah, we'll just stick with that. Okay, you could do another one.
Side, too.
And you also know that OA and OB are both the radius, both the radius. So OA and OB must be equal to each other as well, correct? So there's all kinds of reasons. You could go side, side, side. You could go side, angle, side. You could go, since you know this is equal to this because they're both the radius, you could say hypotenuse leg, couldn't you? Right? Remember we did those? We haven't done those a whole lot. But there's a lot of reasons why this triangle and this triangle are congruent to. I'm sorry. I shouldn't have said that we know that AD and BD are equal to each other because that's what we're trying to show, isn't it? Okay, so it's not. We can't just say it's obvious because that's what we're trying to prove in the first place. So sorry about that. You can't say that we know that AD and BD are equal. That's what we're trying to prove. But I do know this side is equal to this side is equal to this side. I've got a right triangle. There's my hypotenuse. There's my leg. These triangles are congruent to each other. So if the triangles are congruent to each other, all the parts that match up, if I took those two triangles and put them right on top of each other, what must be true? Well, this little angle right here must be equal to this one here. Agreed? If I took those triangles and flopped them on top of each other, wouldn't those match up and be exactly the same? What else must be exactly the same? This little angle is that little angle. And what else? These two sides right here must be equal to each other as well. That's what we're trying to prove, isn't it? All right? We call that corresponding parts of congruent triangles are congruent. Do you remember that? No. Corresponding parts of congruent triangles are congruent. We've mentioned it a couple times. We've mentioned it a few times. If I would teach this like I've taught in the past, geometry classes, we've always done proofs, this would have been second nature to you. I still debate whether I should teach the proofs or not, but I don't know. It takes us long enough to get through what we've gotten through up to this point. It would just take even longer if I went through all the proofs. But anyway, that's good enough. So what did I just do right there? I just proved that AD and BD were congruent to each other, and that shows that that theorem is true. All right? We proved it. Everybody good with that? All right, enough of that. So, but what must be true about the chord and the radius, though? They've got to be what? No, the chord and the radius. They got to be perpendicular. They can be different lengths, okay? Because it looks like that chord right there is a lot longer. I could have taken... Yeah, let's do this. Let's just do it quickly, though. All right, so from here, let's do this. Let's draw the radius here just to make it look a little different than what it did before. Okay, there's a radius, okay, and I want to be perpendicular to another chord. Look, I could have had the chord really, really small, okay, from there to there, okay. So what's true about that chord? That little segment right there and that little segment right there are equal to each other. What did you do to that chord? You bisected it, correct? Okay. Or you could have made the chord from here to here, right? It's a different length, but what's true about this little segment and this little segment right here? They must be equal to each other if the chord and the radius are perpendicular. So if they're perpendicular, then that chord is being bisected. You with me on that? What if we did this? What if I took a chord I don't know, let's go kind of this way, like that. Okay, so I got a chord. What if I take that radius and I'll tell you what, let's do this. I think I might be able to find, yeah, there's the center. See that little dot right there? It's kind of hard to see, but there's a little dot. If I put a dot right there, I just found the center or the midpoint of that chord, didn't I? Okay, so this is another theorem, all right? It's kind of like we switch the if and the then around, all right? So the first one said, if a radius is perpendicular to the chord, then it bisects the chord. This one says, what do you think? If the radius bisects the chord, then what must be true about that radius and that chord? They must, no,
Perpendicular.
they're perpendicular. They're perpendicular. You get it? The first one said, if, listen to me, the first one said, if they're perpendicular, then the chord is bisected. Agreed?
Yes, sir.
This theorem says, if the chord is bisected by the radius, then the chord and the radius are perpendicular. You see the difference? We switch the if and the then around. All right? So this one says, if I know that this and this are equal to each other, then what must be true about the angle that's formed right here? Then it must be a right angle. It seems like a subtle difference, but it's actually a pretty big difference, right? But it's relating to the same thing. Does that make sense? All right. Let's see if. Okay, let's do this one. It's another circle. This one says this. I'm going to read it off to you, this theorem, and then we're going to do an example. We'll stick some numbers in there, okay? It says, the line in the plane of a circle that is a perpendicular bisector of a chord. Now, it says a line, all right? So it's not just a chord, it's a line. It goes through the circle. Okay, it says, if the line, and let's tell you what, before we even do this, let me draw a little dot so I know where the center is. Okay, it says the line in the plane of a circle just means the line is in the circle. That is a perpendicular bisector of a chord. So let's draw a chord. Let's just draw it right here. You could draw it anywhere. There's a random chord in my circle, okay? If I take a line and I draw it, and it's the perpendicular bisector of this chord right there, what does that mean? That means there's the dot, there's the center, or the midpoint of that little chord. Let's put a dot right there. Okay, I kind of messed up my line, but that's okay, it's good enough. So watch this. If I have a line, now I put that in the middle of that chord, so what must be true? That little bit and that little bit must be equal to each other. So here's what the theorem says. Everybody watching? It says if I take a line that goes through the center, I'm sorry. No, we don't know it goes through the center. If I take a line and it's the perpendicular bisector of this chord, everybody hear that? So where would I draw it? Probably about right there, just eyeballing it. Do you agree? So if that's the perpendicular bisector, but remember, it's a line. It keeps on going. So where do you think it's going to hit? It's going to hit at the center. That's right. So let's listen to it again. If you have a line that is the perpendicular bisector of a chord, everybody hear me? Just draw some random chord on your circle. And if you split the chord in half and you make sure that that line is a right angle, guess where it's going to always hit? It's always going to hit right at the center of the circle. Okay? Because if I tried, let's try to do one that is not perpendicular. Let's say we have a line that goes through the midpoint of this chord. So we bisect the chord, but it's not perpendicular. So watch. So that bisects the chord, doesn't it? Okay, but it's not perpendicular to the chord. Is that thing going to go through the center? No, it's not. Okay, the only time it's going to go through the center is if we hit that chord at the perpendicular bisector. And we've talked about perpendicular bisector in another chapter, haven't we? So, and that's pretty easy, right? It bisects the chord and it's perpendicular to it. Everybody with me? So the yellow one, if it's a perpendicular bisector of the chord, it's going to go through the center. The pink one, well, it's a bisector, but it's not perpendicular. It's not going to go through the center. Or we could draw another one that says what? Well, it's perpendicular to it, but it doesn't bisect it, like right there. Thought I'd change the color of that. Let's change it now. Okay. What if I did that? It's perpendicular to that chord, but it doesn't do what? It doesn't split that chord in half. It doesn't bisect it. So guess where it's not going to go? It's not going to go through the center. The only time it's going to go through the center is if you hit the perpendicular bisector of the chord. Okay, enough of that. Let's do an example. And let's put the center in here first. And then we'll draw a radius that goes like this. And then I'm going to draw a chord. Like that. Okay, and here's what they tell me. They tell me that it's perpendicular. Okay, so we know something about that, don't we? Radius and a chord being perpendicular to each other. What does it do? It bisects that chord, doesn't it? All right, so we know that. And then let's put some stuff in here. We're going to put some numbers in here this time. All right, so we're going to use all that stuff that we just learned. We're going to put it into practice, and we're going to try to find some missing stuff. All right, so here's what they tell you. Let's go to a different color. Green. Can you see that green? Yeah, you can see that pretty good. All right, let's see. They tell you that OD is 3. So that little bit right there is 3, from O to that point. Everybody see that? They also tell you that AB is 8. So AB, from there to there, is 8. And they want you to find the diameter of the circle. The diameter of the circle. So where is the diameter? Well,
No.
it would be... No, AB is not the diameter. The diameter has to go through where? The center. Can you let her? Right. So is the diameter even drawn on this?
No.
No. So if you wanted to, you could draw it, couldn't you? But if I could grab it. Did I grab it? Can't see. There we go. I think I grabbed it now. No, it's not what I wanted. Anyway, let's see. Yeah, there we go. And let's go right to the circle. Okay, there we go. So I want to find that whole entire thing. But did I really even have to draw it? Not really, because if I know the radius, then how would I find the diameter? Just double it. That's right. Multiply it by 2. Okay, everybody with me? So let's everybody look. So what in the world are we going to do? How in the world are we going to find the diameter? Well, we got to find the radius, don't we? Well, do you see a radius here anywhere?
Yeah.
OC. But is there any way to find OC with what I have drawn right now? It's really not. I do know something, though. I do know that AD and DB are equal to each other, right? Okay, and so that would be 4. Okay, so I know that's 3. Now listen, we just talked about something. I think it was in the last chapter. We just talked about something that makes it really easy. Exactly right. The 3, 4, 5, what? Triangle. Do I have a triangle, though, here?
No.
Let's make one. Okay, so let's go from OA.
And that's the radius.
That's the radius. Exactly right. Now you're seeing it. So look, I've got 3. So look, I've got 3. It's a right triangle. One side is 3, one side is 4, one leg. Let's say a leg. This is 3, this is 4. Then what's OA? It's 5. Now the question says, what is the diameter? That's right. So the diameter is twice the radius, right? If the radius is 5, the diameter is what? 10.
Why the heck are they putting all this stuff?
And that's it. It is that easy, isn't it?
They put all this stuff in.
Yeah.
What if it's
Well,
not
I didn't know, did I?
3, 4, 5 triangle.
What if it's not a 3, 4, 5?
Oh, yeah.
Use Pythagorean theorem. It's a good question. Okay, what if it's not a 3 and a 4? Okay, they made this super easy for you, right? Because you should recognize 3, 4, 5. But if you wanted to, you could always go 3 squared plus 4 squared equals, I don't know, we'll call it d squared for diameters. Or actually, let's call it r, because that would be the radius, wouldn't it? Let's call it r squared. Is that all right? Let's do it super quick. 3 squared is 9 plus 16. And then we take the what? Square root. Square root of 25 is 5. Okay? But why bother doing all that when you saw it's a 3, 4, 5 triangle? Agreed? That's why.
But when it's not like one of those triangles.
Then you do the Pythagorean theorem, right? If they give you some crazy random numbers, then you would do Pythagorean theorem to find this. And then you double it. Make sure you double it because they're asking for the what? The diameter of the circle. Now do you see how all this stuff is coming into play? Sure. All right, let's do another one. This one, we're going to compare 2 circles to each other. Okay, let's scooch that over. Let's scooch this over. Okay. Okay. So now watch. It's kind of the same. It's kind of the same thing as what we did before. So let's draw a radius. Let's draw a chord right there. Okay? And let's label these things. You should be doing this as well. Q, R. Because I'm gonna write down some stuff here, and then X is right there. Okay? And let's do the same thing over here. But I'll tell you what, let's do this. Copy, paste. I was thinking about having these things already drawn for you so I don't have to take the time, but 90. What? Oh, I know what I want. Sorry. Let's try this again. Let's transform. Let's rotate. Let's just rotate it 90 degrees. That's what I want right there. Now, if you notice what I did, I don't know if you noticed or not, but I took QR and I copied it and I pasted it and I just flipped it. So what do you think is true about QR in this line right there? They're equal to each other. Okay? So PN. And we'll talk about what we're going to do here in a second. And we got a dot right there. Let's make a radius that goes to there. All right. We're almost ready. You drawing this down? You're writing this down, I should say. And this is, what is that, U? All right. These are the letters that they use. All right. Here's what the theorem says. Ready? I got everything labeled, I think. And I didn't say that this was right. Okay. It's not really that hard. We're just comparing 2 circles here. It says incongruent triangles. So it says that these triangles are congruent. What would that mean? If the triangles were congruent, they're exactly the same. What must they have that's true about both of those triangles?
Same radius.
The same radius. Very good. Okay, they must have the same radius. So what do you think is true about AZ and BU? They must be equal to each other. That's right, because it tells you right at the beginning that the triangles are congruent. Okay, so they got to circles. All right. Okay. All right. Yeah, I said triangles. I meant circle. Thank you. So the circles are congruent to each other. So that must mean they have the same radius. All right. So we know that. Now, it says incongruent circles, 2 chords are congruent if and only if they are equidistant from the centers. Remember we talked about a point and a line and the distance? What is the distance from this point to this line? Is it from there to there? Is that the distance? Is it to the end of it? It's perpendicular. Exactly right. It is. You're exactly right. It's basically altitude, okay? So the distance from a point to a line is the perpendicular distance. So let's read the theorem again. It's in the book if you want to read along. It says, incongruent circles, which we have here, 2 chords are congruent. The 2 chords, what are the 2 chords here? QR and PN, if what? They are equidistant from the center, all right? Now, what does that mean right here? Equidistant from the center. The same distance from the center, but what distance though? It's the perpendicular distance, okay? So here's the center, here's the chord. How do I measure the distance from A to this line segment QR? I measure it as a perpendicular distance, okay? So what they're saying basically is that AX and what else over here must be equal to each other. BY, right. BY must be equal to each other. All right. Now, again, we didn't know that to begin with. Okay. We just knew if these are perpendicular, then we know this and this are equal. Agreed? And if they're congruent circles, tell you what, let me write this down. I'm going to scooch this up just a little bit. All right, so here's basically what you know. I'll write it down like this. There's two things that you know. Here's number one. Okay, so if AX equals BY, this is basically what the theorem says, but in letters like this, okay? If AX equals BY, then those two big chords must be equal to each other. So what is that? QR must equal what? PN. That's the chord, right? PN. That's the first thing it says. So it says if this little segment right here from A to X, that's the distance, right? So the distance from the center to the chord, if those two distances are equal to each other, then what's true about the two chords themselves? They got to be equal to each other. Everybody see that? So if AX is 5 and BY is 5, what must be true about QR and PN? They must be equal to each other. Does that make sense? Okay. So let's do part 2 of this. So part 2 says it switches it around. The if and only if means like that. So instead of if AX equals BY, what are we going to say now? If QR equals PN,
Then AX equals BY.
that's right, then AX equals BY. So the second part of the theorem says if the two chords are equal to each other, and this is perpendicular right here, what's true about the distance from the center to the chord? Then they're equal to each other, all right? So if I told you that QR, whoops, that was ugly, was 5 and PN was 5, what does that mean about AX and BY? Then they're equal to each other. So if I said that that was 3, what could you tell me about BY? That was 3 as well. Everybody with me? Okay. There's 2 examples that they do in the book, and I'm not going to have enough time to do those examples. So what I'm going to have you do is I want you to look over examples 2 and 3. Examples 2 and 3. Okay, it's pretty simple. It really is. It's pretty basic. It's not that difficult. Example 3 is a little bit harder than example 2, but I want you to look over that before you do your homework. And here's your homework. It's section 8.1. No. This is on your own. Just put it in your notes. Okay? Put that in your notes. And then your homework is page 348. And it's 10 to 24. Make sure you go over those examples, though, okay? It's really important. I really think that you can figure it out on your own if you just read the examples.